Okay, this is going to be part 9 of the series on trigonometric integrals. This time we'll look at secant and tangent again. Now in the previous videos we've looked at a couple of these rules here, where we had an integral of a secant raised to a power times a tangent to a power. And we looked where the secant was even and you had a tangent and you followed rule 1 here. Then we did where the tangent was to an odd power and followed rule 2. And if you haven't done it, I would definitely watch those previous videos to see how these work. Now in this video, what we're going to look at is this, kind of another option on this. Suppose you had either the secant to an even power with no tangent, or the tangent to an even power with no secant. And you approach it a little bit differently, so we'll look at that in this video. Now in this one, we'll look at the specific example will be the tangent to the 4th power. So we'll pretty much ignore these rules, but still just use some common sense in how you go about it. Now we'll still have to use some identities, so let's look at those. These are the identities we used in the previous videos, just a reminder. Secant squared is 1 plus the tangent squared, and the tangent squared is the secant squared minus 1. Also a reminder on the derivatives. The derivative of the secant is the secant tangent, and the derivative of the tangent is the secant squared. So you'll need these as we go through this. So now with all that in mind, let's go ahead and let's take a look at our sample problem. Okay, so the sample problem is going to be this. What we've got is tangent to the 4th power. Now again, there's no rule for the tangent to the 4th power, but the best you can do, you've got an identity for the tangent squared. So the trick here will be to break this tangent to the 4th into 2 tangent squareds, and then you'll be able to put it into the form of integrals that you can work with. So the very first step here will be to go ahead and just do this. We'll make it be the integral of, and we'll break it into the tangent squared of 3x times the tangent squared of 3x. Now again, why would you want to do that? Because you can use identities then to take these tangents and break them down into the forms of integrals that you actually have an integral that you can work with. Now, at this point, you're going to need identities, so we'll take a look at the identities again just to remind you. The tangent squared is equal to secant squared minus 1. So the next thing we'll do is go ahead and take this second tangent and change it into a secant squared minus 1. So this would be the integral of the tangent squared. And then again, inside parentheses here, we'll change the tangent squared into a secant squared of 3x minus 1 dx. Now again, why are we doing this? Well, basically just to break it down into integrals that we can actually integrate. Right now we're stuck with ones that we can't integrate. So the next step will be to do this. Take this tangent squared and distribute it through the parentheses here. So this will become the integral of, now multiply these two together and you would have the tangent squared of 3x then times the secant squared of 3x. Then tangent squared times negative 1 would give you minus the tangent squared of 3x. And then you'll have a dx over here. Now you're kind of on the way to the right spot. If you look at this one right here, the integral of the tangent squared times the secant squared, you should see something there. The derivative of the tangent will get you to the secant squared, so you're going to be able to do something with this integral using use substitution. But at the moment, you can't do anything yet with the tangent squared because you don't have an integral that will work with this. So the trick here again is to use a second trig identity. So we'll make a second substitution here and change this tangent squared into a secant squared minus 1. So again, we'll leave this one alone because we can work with this. So this will become the tangent squared 3x times a secant squared 3x. Then you've got minus, and change the tangent squared again into a secant squared minus 1. And then put a dx out here. Okay, the next thing to do, let's go ahead and distribute this negative. So this is going to become the integral of the tangent squared of 3x times the secant squared of 3x. and distribute this negative. So this will become minus the secant squared of 3x. And then two negatives make a positive. This will turn into a positive 1 dx. So you've got that. Now what you've got here, all three of these are things you can work with. Here's the integral of three separate things, and we can break them into three separate integrals because each one of these you can solve. Using u substitution on this one, the derivative of the tangent will give you the secant squared, so you can make this one work. If you take the integral of the secant squared, that will be equal to the tangent, so that'll work. And the integral of 1, you've got a power rule for that, so that will work. So the next thing to do is go ahead and take these and split them up into three separate integrals. So we'll come down here, and rather than having one big integral, we'll make it be the integral of the tangent squared of 3x times the secant squared of 3x dx. So there's the first integral. And then minus the integral of the secant squared of 3x dx. And then finally plus the integral, if I put it in there, of 1 dx. So split it up into three separate integrals. Now, why would you want to do that? Because now you can solve each one of those separately, but two of them are going to require u substitution. Now, on this one, you can think of this as being, and I think I'll just rewrite just this one. Think of this one as being the integral of the tangent of 3x quantity squared times the secant squared of 3x dx. So again, if you look at it like this, it'll make it a little more obvious what the choice of u is. So this will, we'll go ahead and put these other ones on here too. So secant squared of 3x. And then finally, the integral of 1 dx. Okay, let's take care of the u substitution next. Now again, treat each one of them as a separate problem. So on this one right here, if you let u be equal to tangent, then the derivative will get rid of this part right here in u substitution. So let's do the u substitution. So this has become u is equal to the tangent of 3x. So du dx would be equal to, now the derivative of the tangent is the secant squared. But don't forget that's a composite function. 3x, the derivative of the inside part would be a 3. So that gets you to du would be equal to, now I'll take the 3 and move it in front. 3 times the secant squared of 3x dx. Now again, you don't need this 3, so move it to the other side, and you wind up with 1/3 of du would be equal to the secant squared dx. Now again, this matches up with this right here, so on this first integral, that's going to be your u substitution right there. Now let's take a look at the second integral. You've got an integral. The integral of the secant squared is the tangent, but this time you're going to let u be equal to the 3x on this problem. So we'll let u be equal to 3x. So the derivative of u with respect to x would be equal to 3. So du would be equal to 3 dx. And you're trying to get rid of a dx right here and change it into a u problem. So move the 3 over, and on this integral, you get 1/3 du would be equal to dx. So that matches up. So on this one, there's the substitution right there. Now finally on the last one, you will not have to use u substitution because that's just the power rule. So we'll bring it down and continue on. Okay, let's finish this one. This will turn into the following. It'll be the integral. Now this will turn into u squared, and then in place of the secant squared, you're going to put 1/3 du. So that'll be 1/3 du right there. Then you've got minus the integral of, and this is going to be the secant squared of u, and again, in place of dx, you'll put 1/3 du. So treat each one as a separate problem. And then finally out here, you're going to have plus the integral of, and we'll just put 1 dx. So no u substitution on this last one. Okay, bring the 1/3 out in front. So this would be 1/3 the integral of u squared du minus, again, bring the 1/3 out in front. So the integral of the secant squared du. And then finally, this one, we can just go ahead and go. On this one, the antiderivative of 1 would be x. And then for all of these, we'll tack on a plus c at the end. Okay, so this one will turn into 1/3. And this will be of u cubed divided by 3. Then minus here, you'll have 1/3. And the integral of the secant squared is the tangent of u. Then you've got the plus x. And then finally, you've got a plus c on the end of the whole thing. And finally, the very last step now is to just go ahead and replace the u's with x's. So the final answer, you can put these two together, and you would have 1/9. And in place of u, put what u is equal to. And on this problem, u is equal to the tangent of 3x. So this will be the tangent of 3x cubed. Then you've got minus 1/3 of the tangent of, and replace u with what it's equal to. Here, on this problem, u is equal to 3x. So we'll put a 3x there. And then finally, you've got this plus x, and finally a plus c to account for a constant. So that's going to be the final solution to it right here. Okay, now again, real quickly, let's run back up and just look at it from the beginning. So the idea is starting with a tangent to the fourth, split it up into 2 tangent squares. Now the reason you're doing this, you're trying to change them into integrals that you can actually integrate. And then using an identity, change this tangent squared into this, secant squared minus 1, using this identity over here. Then distribute, and again you come up with a tangent squared, so use a second identity right here. Now what that does, finally it gets you 3 separate integrals, but you can actually integrate each of those. You'll have to use u substitution on 2 of them. So as you follow it up, just do the u substitution, then finally put all 3 solutions together, and your final answer will be this right down here. So what that is, that's an example of how to handle just the tangent to an even power. Now in the next video, we'll look at how to handle the secant to an even power, but it'll be a process very similar to this.